Hello, this is a Bullis Student Tutor, and today I will be discussing the solubility product constant, noted KSP. So, this is simply the equilibrium constant for a reaction of a compound dissolving in water. Now, on the left side, we'll have a solid, and on the right side, we'll have the products, which are the ions that it dissolves into, which are going to be aqueous because they're dissolved in water. And when writing the equilibrium constant, KSP will always take on a similar form because the left side, the reactant is a solid. That won't appear. So all we're going to have is the product of the products, so lead 2 plus and iodide, raised to their stoichiometric coefficients. Lead 2 plus has a stoichiometric coefficient of 1, iodide has a stoichiometric coefficient of 2. So KSP will be the concentration of lead 2 plus times the square of the concentration of iodide. So as an example, we're going to find what is called the molar solubility of silver chloride, given its KSP. And to do this, all that we do is we set up an ice table. So initially, we'll say we have some silver chloride that is going to dissociate. So 0 will be the initial concentration of both ions because it is not yet dissociated. We're not even going to worry about silver chloride on the left because it's a solid, so it's not going to contribute at all to the equilibrium constant. And now we're going to add an X as it dissociates, so we'll have a final concentration of X for both silver and chloride. And this X is what is called the molar solubility. So now we'll set up, we know KSP is equal to, so we have each product raised to the power of its stoichiometric coefficient. Those stoichiometric coefficients are all 1, so we just have silver times chloride. And we have that both are equal to X, so we actually have X squared. And because we're given that KSP is 1.6 times 10 to the negative 10th, we can actually find that X is equal to 1.3 times 10 to the negative 5th moles per liter, and that is what is called the molar solubility. Okay, as a final example, say that we're given the molar solubility of magnesium fluoride is 1.2 times 10 to the negative 3 moles per liter, and we're going to find KSP. So to do this, we set up another ice table, and similarly, we're just going to say both concentrations are 0 on the right there. And so once it dissociates, we're going to add 1.2 times 10 to the negative 3 moles per liter of magnesium 2 plus. That's what the molar solubility represents. And for fluoride, actually, we have to add 2 times that, because we have 2 moles fluoride for every mole magnesium 2 plus, and so what that means is that we have 2.4 times 10 to the negative 3 molar. So the final concentration will be 1.2 times 10 to the negative 3 moles per liter, and 2.4 times 10 to the negative 3 moles per liter. So this is at equilibrium. And so now we're going to find KSP. So KSP in this case is just magnesium 2 plus raised to the power of 1 because its coefficient is 1. But fluoride's coefficient is 2, so we have to square that. And so all we have to do is 1.2 times 10 to the negative 3 times 2.4 times 10 to the negative 3, but we have to square that. And we will find, or at least we should find, that the KSP for magnesium fluoride is 6.4 times 10 to the negative 9th. And we are done.